Hello, everyone. Welcome to today's Quantum Spacetime seminar. We are very happy to have Gary Horowitz from UCSB, who would be telling us about a new type of extremal black hole. Over to you, Gary.
Okay, thank you. It's a great pleasure to be able to give this talk. I just wish I could be there and see you all in person. Okay, so let me share my screen. Okay, so I'd like to tell you about some work I did recently with Oscar Diaz and George Santos, which is described in more detail in these two papers that we put out last fall. This work contained a couple of surprises, which I'd like to tell you about. First of all, let me say, feel free to interrupt with questions at any time. I'll be happy to answer them. And I have to start with an apology, because I know this seminar series is called Quantum Spacetime, but my talk will be entirely classical. Okay, so I'm going to consider standard four-dimensional asymptotically flat black holes. Nothing exotic like asymptotically anti de Sitter or higher dimensions or lower dimensions, just the standard good old four-dimensional black holes. And as you know, in Einstein-Maxwell theory, there's a maximum charge that can be carried by a black hole of a given mass. And these extremal black holes are characterized by having a horizon with zero Hawking temperature. So if you don't have highly charged particles, Hawking radiation will decrease the mass and you will approach one of these extremal black holes, and that's a natural end state for Hawking evaporation. Now, there are no Hare theorems which show that if you add simple matter, like free scalar fields, nothing changes. The scalar field radiates off to infinity or falls into the horizon, and you end up with the same type of extremal black holes. But for more complicated matter, there are changes. We know that in supergravity and string theory, there are dilatons, which have exponential coupling to the Maxwell field. And in this case, the horizon often becomes singular in the extremal limit. And the reason is that the Maxwell field now acts as a source for the scalar field. In the extremal limit, the horizon moves infinitely far away. And so the source acts for a very long time, driving the scalar to very large values, causing the horizon to become singular. Well, I'm going to consider a theory with a Maxwell field and a charged scalar that has a new kind of extremal limit. The black hole with maximal charge for a given mass is non-singular and has a non-zero Hawking temperature. And we call these objects maximal wormholes. And this raises a puzzling question, because if you Hawking radiate toward one of these maximal wormholes, the temperature is non-zero, you would think you would keep radiating and possibly turn this black hole into a naked singularity. Well, I'm going to argue this doesn't happen, but we'll see why. So the outline for the talk is that I'm going to start by describing the theory I'm going to consider and this new type of extremal black holes. I'll then discuss what happens, or what we think happens during Hawking radiation. And then finally, I'm going to look inside the horizon of these new black holes, and we'll see some new and surprising features. Okay, so the black holes I'm going to consider have scalar Hare. And so we first have to ask, when can a static scalar field exist outside the horizon of a black hole? Back in the 70s and 80s, Jacob Bekenstein proved various theorems saying that scalar fields of certain types cannot exist. These are part of the no-Hare theorems. But it was shown in 2008 that in ADS, in asymptotically ADS space-time, ordinary charged black holes, the Reisner-Nordstrom anti de Sitter metric, becomes unstable at low temperature to forming charged scalar Hare. And this was discussed in these papers and formed the basis for the holographic superconductor story. So these new kinds of hairy black holes were the gravitational dual of a superconductor, and the charged scalar Hare was just the representation of the charged condensate when the Cooper pairs or in the superconductor. Okay, but more recently, it's been shown that asymptotically flat black holes can develop scalar hair in various situations. First of all, if the scalar is coupled to a Gauss-Bonnet term. So there were 3 papers late in 2017 by 3 different groups showing that this happens. Even for Schwarzschild black holes, you can get scalar hair. But these theories have higher derivatives. I'm not going to consider those. But then a little bit later, it was shown that you can get hairy black holes if you couple the scalar to f squared, just the square of the Maxwell field. And the basic reason is that for an electrically charged black hole, f squared is negative. So it acts like a negative scalar potential near the horizon. And that can overcome a positive mass for the scalar field and destabilize the black hole, causing the scalar field to turn on.
Sorry, Gary, can I just ask, I'm sure you elaborate, but this is the last example is for a uncharged scalar or a charged scalar? The one where you get in asymptotically flat space also, this hair?
You can do it in either case.
I see.
I'm going to consider a case with a charged scalar, but this first paper was discussing neutral, uncharged scalars.
I see.
And if you couple, if you just take a massless neutral scalar and couple it to f squared, you will find that it, you can get, okay, hold on, let me go back. You find that you can get hairy black holes.
I see.
I'll discuss it more, yeah.
Thank you.
So here's the model. The action we're going to consider has a standard Einstein-Maxwell piece, a standard charged scalar field with mass m and charge q. So the script d here is the usual grad minus iqa, and the Maxwell field is just the curl of a. And then we add this one new interaction. So we're going to add an f squared psi squared term. We're going to couple the scalar field directly to f squared, and we're going to give it a coefficient alpha. So alpha is going to represent the strength of this new interaction. And we're going to assume that alpha is always positive. And if it's positive, then this term comes in with the same sign as the usual term, and this action satisfies all the usual energy conditions. So there's no negative energy.
Gary, sorry to interrupt.
Yes.
In sort of studies that were largely situated in ADS, I think there was this old story that extremal black holes tend to develop an ADS2 kind of geometry, and if there's a scalar that goes below the BF bound of that effective ADS2, the black hole becomes unstable. So
Yes.
is something sort of very similar happening here?
Exactly. Exactly similar. I'll discuss it, but that's the origin of the instability here.
Yeah, thank you.
Yes. So yeah, we'll see exactly the same thing. So the equations of motion for this theory are written here. You don't need to worry about the details, but I just will point out we have the Einstein equation on top, and then Maxwell's equation looks like this, and the scalar equation is the last one. And you notice that f squared, appears very much like a mass term. And I said it's negative for an electrically charged black hole. And if it gets large enough near the horizon, this new coupling can overcome a positive mass squared and destabilize the scalar field. So that's the source of the instability we're gonna see. Okay, so we're going to study static spherical asymptotically flat charged black hole in this theory using the standard ansatz. So here's our metric. It's spherically symmetric. It has 2 metric functions, p and g, both functions of r. The Maxwell potential has only a time component. We'll call that phi of r. And the scalar field we can take to be real and just a function of r. So one solution is the well-known Reisner-Nordstrom solution with 0 scalar field, and it takes the usual forms. So P is the usual expression with the inner and outer horizon are plus and minus. The extrametric function g is, of course, 1. And the electrostatic potential phi can be written in this way. I'm going to choose a gauge in which phi vanishes at the horizon, non-zero at infinity. The charge here, so its value at infinity is mu. The charge is mu times r plus. Of course, there's only 2 parameters, not 3. So mu is related to r plus and r minus. In this case, just by mu squared is the ratio of r minus over r plus. And so mu equals 1 in the extremal limit. Now, black holes in this theory depend on 5 parameters. We have the 3 parameters in the action, the mass and charge of our scalar, and the new coupling alpha. And then we have the black hole mass and the black hole charge. But there's an overall scaling symmetry, which will rescale these dimensionful parameters. So we can describe solutions in terms of 4 dimensionless parameters, which we'll take to be the charge to mass ratio of the scalar, the coupling alpha, and the black hole mass m times the scalar mass, little m, and q times m. In a gauge where the electrostatic potential vanishes at the horizon, we're going to set mu in general to be the asymptotic value of this potential. And we can use mu instead of the charge, q, of the black hole. And that'll be useful and an important parameter. Now, in order for black holes in this theory to have scalar hair, there's an asymptotic condition. And one finds that a scalar field can be bound to the black hole only if this is satisfied, only if the charge and mass of the scalar field are related to this sort of electrostatic potential mu in this way. Q squared mu squared has to be less than or equal to m squared. So if Q squared mu squared is strictly less than m squared, the scalar field asymptotically falls off exponentially, as shown here, where this parameter eta and b are just constants. So it's falling off exponentially, showing that the scalar is indeed bound to the black hole. If q squared mu squared is equal to m squared, the asymptotic behavior is a little more complicated, but it still falls off exponentially. In this case, like e to the minus the square root of r. But notice in this case, you have a further condition that the black hole charge must be bigger or bigger than mu, mu times the black hole mass. If this condition is not satisfied, this if you try to write down a static scalar field, it's going to oscillate asymptotically, and the solutions will have infinite mass. So let's first look at this condition for instability. When does Rysberg?
Quick question, please, Gary.
Sure.
Q squared mu squared being greater than m squared, isn't that also the condition for a superradian to turn on?
Let's see. If let's see, Q squared mu squared greater than m squared. Yes, that would be superradiant.
So you say that you can have hair only when superradiance is not possible.
Yes.
Okay.
Right.
That's very interesting. Okay. And one more question. If Q is 0, Q is, if I understood right, the mass of the charge of the scalar field.
This little q is the charge of the scalar
little q, yes.
Yeah.
So if Q is 0 and your particle was not tachyonic, your condition is never met.
Sorry, no. If Q is 0, this condition is always
met. Sorry, always met. Oh, sorry. Yes. Okay, so uncharged scalars very easily obey your condition. I see. Thank you.
Right.
Okay, thank you.
Yeah. In fact, the first paper from 2018 discussing this type of hairy black hole looked for neutral, discussed neutral scalars. Yeah, and didn't have to worry about this condition, right? Okay. Okay, so that's the asymptotic condition. And now we're going to start to look at this instability, and we'll first consider just the linearized case. To see if Reisner-Nordstrom can be unstable, it's natural to start with the extremal solution. After all, the instability is driven by the electric field near the horizon, and the extremal solution will have the largest charge and the largest electric field. So we first consider the extremal Reisner-Nordstrom. And as you know, this has a near horizon geometry, which is ADS2 cross S2, with the two-dimensional ADS scale set by the horizon radius. And as Shiraz was saying earlier, neutral scalar fields in ADS are unstable if their mass squared is less than the so-called Brightman-Friedmann bound, which is some negative mass squared. And in ADS2, this condition turns out to be that the m squared times the ADS radius squared must be less than -1/4. In our case, we have a charged field, and they get extra contributions to their mass from the coupling to the vector potential. And in our theory, there is a further contribution to the effective mass in this near horizon region from the scalar coupling to f squared. So when you work it out, the BF bound will be violated if this condition is satisfied. So you'll recognize that the first couple terms, the 1/4 plus m squared L squared, are just the conditions, being less than 0, is just the usual condition for the instability of a massive neutral field. You then get a correction due to the charge on the field, and another correction alpha to alpha due to our new coupling. So the BF bound in this ADS2 is violated if alpha is bigger than this expression here. Now, I'll remind you that the extremal Reisner-Nordstrom solution has mu equal to 1. And the asymptotic condition to get scalar hair requires then that m squared is bigger than q squared. So this is always positive. And so we get a positive lower bound for alpha. If alpha is big enough, if it's bigger than this lower bound, we know that there will be an instability near the horizon. The scalar field is stable at infinity, has just the usual positive mass. So the black hole is expected to develop hair. So when that condition for the instability, when this effective mass is less than the BF bound, is satisfied, we expect to get the instability of the extremal solution. The onset can be, will happen for some q less than m. And in that case, you can find it by looking for a static zero mode, a static finite energy linearized solution for the scalar psi. And we've checked that these zero modes really do mark the transition between stable and unstable quasi-normal modes. So I'll remind you, a quasi-normal mode is you take a field, you add this e to the minus I omega t time dependence, demand that the field is ingoing at the horizon, outgoing at infinity, and you find solutions only for discrete frequencies. Here's an example with these parameters indicated on the lower right. The lowest quasi-normal mode is plotted here as a function of mu. As we increase the charge, mu increases to 1. The green line, the green curve, is the imaginary part of the frequency. The blue line is the real part of the frequency. And you see that below before you reach a value of about 0.97, the imaginary part of the frequency is negative. So these modes are stable, they're damped. After that point, they become positive, indicating a growing mode. And the zero mode is the red dot right there. Okay, so you...
Sorry to constantly interrupt, Gary.
Please.
I'm trying to confirm I'm understanding. So suppose your coupling alpha was large enough, but q mu was greater than m, so that that the earlier condition you talked about was not satisfied. then do I understand right that the scalar continues to be unstable, but it's also unstable at infinity? It just sort of tries to condense everywhere. Because the scalar is effectively tachyonic even at infinity, just because this, the effective mass from coupling to the chemical potential overwhelms the mass, the intrinsic mass. So in this case, it continues to be unstable, but even infinity is unstable, so you're not interested in it. But you're most interested in the case where it's stable at infinity, but unstable near the black hole. Is right?
Right. Yeah, that is true. That's what I'm interested in. I think in your case, we would have the sort of super radians, but we have this extra instability near the horizon.
Sorry to interrupt, but it seems to me that the field would also, at least be unstable even at infinity, right? In that case, wasn't that the point of your exponential being not oscillating, but growing or decaying?
Right. So in order for the scalar to be bound to the black hole, we need this exponential decay, and we need this asymptotic condition where Q mu is less than or equal to m squared. If you violate that, what I said with static solutions will oscillate indefinitely, indicating that they have infinite energy. Let's see.
Could I say it once more, please? I'm sorry to constantly interrupt, but if we think of this as being like a thermodynamic ensemble set by boundary conditions at infinity, then the Boltzmann weight for a scalar field, which is e to the power minus beta e plus e to the power beta qm, would turn positive rather than negative when q mu was greater than m. And so it would seem to me to indicate just that the whole thing was unstable, even all the way up to infinity.
The ensemble is unstable, right? That ensemble would not exist. The grand canonical ensemble would not converge.
Yes.
Right, I agree with that. I'm not sure whether just a classical solution would sort of have exponentially growing fields at infinity.
Because the electric field would die out, right? So I don't see that instability at infinity. In the
but there's an effective mass square, which is phi square, A0 square. And A0 is not dying out. That's the chemical potential, right? So I was thinking that phi square, A0 square would beat the m square. That's in fact precisely the mu squared, q squared greater than m square condition. So I was thinking that would you had the effective mass even at infinity would be negatives. Mass square would be negative. But I could be wrong about that. Sorry about that.
Yeah, I think that's right. I think that could be an instability asymptotically. We've not, we weren't looking at that. But that actually might be interesting for something that comes later. We'll come back to that. But yeah, we didn't really consider that case, that possibility.
Thank you.
Okay. All right, so this is the onset of the instability. And now we basically just go ahead and numerically construct the full nonlinear solutions describing these black holes with scalar hair and study their properties. And what you find is the following phase diagram. So this is a case where the new coupling is 1, the charge to mass ratio on the scalar is 1. And what I'm plotting here is just the mass of the black hole in the horizontal axis and Q minus M on the vertical axis. So Reisner-Nordstrom black holes exist in this region in green, basically everywhere below this line 0, where Q is equal to M, because everywhere where Q is less than M, so the difference is negative, we have the standard Reisner-Nordstrom black holes. The blue line represents the onset of this new instability for the scalar field. So that has this behavior, and everywhere above it, you find black holes with scalar hair. So this brown region is the hairy black holes. If you continue to increase the charge, you find a boundary. On the left, this black line is where the horizon becomes singular. So this is a more familiar extremal limit for hairy black holes where the scalar diverges. I mean, the horizon becomes singular. But on the right, what happens when you increase the charge is that you hit the maximum allowed mu for our asymptotic condition. So when Q over M is 1, the maximum mu is 1, and you hit a boundary where mu is equal to 1. Now, notice that these hairy black hole solutions exceed the usual extremal bound. So I said that this is Q minus M, and everything up here has therefore Q bigger than M. The scale is small. These numbers are 0.02, 0.01. So it's not exceeding it by a lot, but it is having Q bigger than M. And the reason why is not surprising. Well, first of all, our scalar can carry charge. So we can have charge carried by the scalar field outside the horizon. But even black holes with neutral scalars can have Q bigger than M, because in this theory, the conserved charge, because the coefficient of F squared is 1 plus this 4 alpha psi squared, the conserved charge is this integral. Whereas the actual charge on the horizon is smaller. That's just the integral of the dual of F over, say, the bifurcation sphere or a cross section of the horizon. So you might expect this black hole charge can get as big as M, and then the conserved charge at infinity can be a bit larger than M. And that's what we see. And I just note that this neutral case with massless fields was studied earlier.
Sorry, how should I think of that physically? Should I think of part of the charge as lying outside the black hole?
How do you think about this physically? Well, let's see. Here is the conserved quantity. So if the scalar field is non-zero, yeah, I mean, the charge you measure at infinity is, well, it's let's see. Psi goes to 0 at infinity. So they agree at infinity, these two expressions for the charge. This is the one that's conserved for smaller radii. This is what we would normally call the charge on the black hole. So I guess, yes, in some sense, the difference must be outside.
Sorry, Gary, can I ask a question?
Sure.
For the charge carried by the black hole, should we evaluate the first quantity with psi taking its value on the horizon?
Yeah, that's right. Well, okay, so this is a constant. You can evaluate it anywhere you want at any radius. That's the conserved charge. So it doesn't change. I'm just saying that, normally, if we want to know what the charge is enclosed, we would write down something like this.
True.
So that's
True. I see. But okay, and of course you have to go on, but just could it be that we say that the integral of the first quantity on the horizon is the charge carried by the black hole, and the same quantity integrated at infinity is the full charge, and the difference is the charge carried outside the black hole? Would that be a reasonable interpretation? Because the top quantity is what's conserved, it seems, right?
right.
It's conserved. So it's the same with radius.
It's the same. It's independent of radius. That's what I mean.
I'm sorry. I got messed up. Yeah. Sorry. Thank you.
Okay.
Thank you. I understand what you're saying.
All right. But let's go back now.
Sorry, I have a naive question. If the first conserved charge, if psi bar square vanish at boundary, then that means the conserved charge, as you measured around the infinity, is same as the conserved charge at horizon, right? QH is very similar to the conserved charge you wrote above.
That is true.
So how does this? I mean.
Okay. So how does this apply?
Yeah.
Okay.
Sorry. 1 second. How does this say that the Q has to be greater than M?
Okay. So this, well, F is different. right? The integral of star f at infinity is not going to be the same as the integral of star f at the horizon.
Okay.
Right? So at infinity, psi is 0, you get a similar expression, but it doesn't mean that that answer is the same as this answer.
Okay, okay, yeah, now I understand. Okay, fine.
Okay, well, let me go back and now what we want to do is look at properties of these black holes. So we look at the mu equals 1 black hole and plot here some of the properties. Here's the entropy, basically the area over 4 of black holes along that red curve. The entropy is non-zero. It's as you go toward the black curve, where that red curve meets the singular solutions, the entropy goes smoothly to 0. On the upper right, we have the temperature, and the temperature is not 0. As you come in, it increases and then goes to 0 as you hit the singular limit. And so these are indeed, they have maximum charge in this theory. We can't exceed this mu equals 1 bound, but they're non-singular with non-zero temperature and entropy. And so this is the new kind of extremal black hole that we're calling maximal wormholes. On the lower plots, I plot on the left here the electric field on the horizon. This is f squared on the horizon as a function of mass along that red curve. And on the right, this is the charge inside the black hole. So this is basically the integral of the dual of f over the horizon. You notice that the charge on the black hole goes to 0 almost linearly as we decrease the mass. But since the area of these black holes are also decreasing almost linearly, the electric field on the horizon stays approximately constant for a while. But then as you approach the singular endpoint, the electric field grows very quickly. That large electric field, of course, increases this instability and causes the scalar field to grow and takes the charge, the charge on the black hole, then rapidly goes to 0.
Sorry, Gary, very sorry. What value of little q is this for, or I'm missing something here?
This is for little q over m equal to 1.
Oh, okay, I see.
Okay. Yeah, so I'm looking for q over m on the scalar field equal to 1. So this asymptotic condition is saturated at mu equal to 1. And that mu equal to 1 curve is the upper limit of this phase diagram, where we,
Oh, I see, I understand. I see, okay.
So, I have another question about this new type of extremal black holes. This is, in usual extremal black holes, we have when temperature equals to 0 as well. And that relates Q and M charge and mass of the black hole also. But in your case, if you have a temperature 0, you still have 2 independent parameters, right?
So you're saying if I have temperature 0, I said these black holes, well, there's 4 parameters total. 2 of them are parameters of the theory. So we can choose alpha and q over m. Those are just parameters in the action. And then we have 2 more parameters describing the black hole, basically their charge and mass.
But your extremal limit does not mean temperature equals to 0. That's that I understand.
No,
but
right. So in this, go ahead.
Yeah, but in your case, temperature equals to 0 limit should exist in some way with capital Q and capital M as independent parameters.
I don't think so. The hairy black holes in this brown region, once you turn on the hair, the temperature does not reach 0. The temperature only reaches 0 back along this line. When you approach the singular limit, the temperature goes to 0.
Okay.
And sorry to confirm, just follow up on that. The red curve is where mu q is equal to little m, right?
That's right. That's right. Yeah.
So if you try to go further to lower the temperature even further, what would have happened is that mu q would have become larger than little m, and you discard those solutions. Is that
right? So then the scalar field's not bound to the black hole anymore.
Right. Thanks.
Right.
So, sorry, Gary, can we come back to your last slide just once with the
this
plot?
one?
Yes, please. So if I understand, if you choose some reasonable, some values of little m times big M sufficiently to the right, you have a nice extremal limit where the entropy is big and so on, and some non-zero temperature.
Right.
And you might come to this, but is the thermodynamics, a good approximation in the sense that the specific heat and so on is much bigger than 1, so that we understand by temperature what we normally mean in a good stable thermodynamic situation? Because sometimes as you know, for say dilatonic extremal black holes, the entropy can even go to infinity, but just the thermodynamic approximation is breaking down. And I was wondering whether that's what's happening, but you might come to it. But anyway, just to ask you.
Right. Well, okay. So first of all, there's a problem in asymptotically flat, black holes, that you never really have stable, ensembles. I mean, if you try to put a black hole in thermal equilibrium, you have energy density all the way out to infinity, and that gravitates, and you get cosmologies. You don't get, really static solutions. You need to put the black hole in a box.
In a box, I see. These have yeah, I guess they have negative specific heat because entropy is going up sufficiently to the right as the temperature is going down.
Right. So this would be negative specific heat. The temperature is going down when you increase the mass. It's positive on this side.
Yeah.
And so the fact that the temperature is not monotonic is very reminiscent of if you take an extremal Reisner-Nordstrom black hole, keep the charge fixed and just increase the mass, right? The temperature goes up for a while and then falls back down again. Right. So we're now seeing a similar type behavior in a class of sort of extremal black holes, or at least black holes that have the largest mass the largest charge for a given mass.
I see.
Right.
Okay. Thanks.
Good. So let's see. So just to emphasize, these maximal wormholes exist due to a trade-off. As you increase the charge, the region near the horizon wants to become singular. I think it's starting to become, approaching a singular state. But if the mass is big enough, before you reach the singular horizon, this asymptotic condition is saturated. And since you can't support the scalar hair if that bound is violated, and there are no black holes without hair having Q bigger than M, the extremal black hole ends up having a positive temperature. So what I want to do now is to look at what happens when we change these two parameters in the Lagrangian. So we have alpha.
Sorry, can I just ask about the terminology that you're using about the extremal? You're calling this extremal. Is that because there's something special happening at the near horizon geometry, or I was just wondering why you are calling it extremal? And of course,
okay, they're black holes which have maximum charge for given mass.
And
so when we were thinking of a name, we decided not to call them extremal. We were calling them maximal wormholes because they have maximum charge and they're non-zero temperature. So we thought that was a more appropriate name. But they are really, they are the analog of extremal black holes. They have maximum charge for a given mass.
I see.
But they do not have this.
Yeah, the near horizon geometry is not ADS2.
It is not ADS2. There's a temperature. It's not a degenerate horizon. So it's not a usual extremal black hole. That's the whole point of the talk. It's a different kind of extremal black hole.
I see. Yeah, thanks.
Okay, let me now ask what happens when we change the two parameters in the theory. So let's first keep the charge to mass ratio equal to 1 for the scalar and just increase the coupling alpha. And what the plot shows is, again, the difference between Q and M, Q minus M on the vertical axis and increasing mass on the horizontal axis for 4 different values of alpha. The red curve on the bottom is the one we saw before when alpha was 1, and then we increase it to 5, 10, or 100. So you should think, okay, so first of all, these curves, because Q over M is still 1, these curves all have mu equal to 1. That's the maximum electrostatic potential. At infinity is still 1. So all these curves have mu equal to 1. The hairy black holes exist below the curves in each of these theories. And the left endpoint here is connected back to the origin with some singular, a boundary of singular solutions, which I'm not drawing. Okay, so these are the maximal wormholes in these theories. And I guess you can see 2 features of increasing alpha. One is that the amount of charge, the maximum charge on the black hole increases as you increase alpha. That's not too surprising. Increasing alpha increases this instability, driving more scalar field outside the horizon, and the scalar field can carry charge, and the total charge at infinity can increase. The second thing you see is that the minimum mass for this maximal wormhole also increases. So here, when alpha is 1, you can get maximal wormholes as long as the mass is bigger than, I don't know, 0.7 or so. But as you increase alpha, you need masses bigger than 3. And that is, well, I guess can be understood because the horizon is trying to become singular. I mean, with alpha bigger, the effect of F squared is a larger source on the scalar field, driving it to large values as the horizon recedes, and making it easier to form maybe singular black holes before you reach the mu equal to 1. Okay, that's the effect of changing alpha. Let's go back to alpha equal to 1 and consider changing this charge to mass ratio. And it turns out that this new kind of extremal black hole, the maximal wormholes, are very sensitive to changing this ratio of Q over M. So let's see why. So first of all, let's imagine increasing it. Well, if you increase Q over M, then the maximum electrostatic potential mu gets reduced. That's less than 1. And now one finds that hairy black holes only exist if the black hole is small enough. There's actually a maximum mass for any hairy black hole. And the reason is that since this maximum mu is reduced, the maximum electric field on the horizon is reduced. But you need the electric field there in order to trigger the instability. And only small black holes will have a large enough electric field on the horizon to create the instability before you reach this maximum value of mu. So that's one effect. The other effect is that maximal.
Sorry, Gary, small means the total mass of the black hole is sufficiently small. Is that right?
Yes. Yes. I'm saying that the mass cannot be arbitrarily big. It can only be in some range.
Okay, thanks.
Second effect is that the maximal wormholes exist down to arbitrarily small masses once Q over M is bigger than about 1.1. In other words, this lower cutoff that I was just talking about on these mu equals mu max curves goes away as soon as Q over M is bigger than 1.1. And that you can understand because, again, this maximum mu is smaller, you reach it more easily. And so you don't have time for the inner horizon, for the horizon to become singular. If you go the other way, suppose you decrease Q over M less than 1, well, mu max is now larger, making it harder to form a maximal wormhole before the horizon becomes singular. And that increases the minimum mass for them to exist. But there's now also a limit on them existing at large mass. there's a maximum mass for these new objects, because I said that this saturation of mu is only possible if the black hole charge Q is bigger than mu times m. Now that wasn't a problem with if mu max is less than or equal to 1, because all the black holes we were looking at had Q bigger than m, and so they always satisfy this condition. But once you go to smaller Q over m and mu max is bigger than 1, this can be violated at large m. So you only have a finite range of masses where these maximal wormholes exist, and it turns out that they completely vanish when Q over m is less than 0.99. So you decrease the ratio by 1%, and you've already gotten rid of all of them.
But
so, yeah.
Sorry, I got confused by the last statement because I thought the uncharged case also had these kind of black holes. Yeah.
Sorry, the uncharged case, sorry, there, go back. This is what I wanted. The uncharged case has hairy black holes, but they don't have this non-singular solution with maximum charge for given mass. So I don't know if it's been looked at in complete detail, but in the paper of Hedero, when they first discussed this with the neutral scalar hair, they say that the maximum charge black holes are all singular in that case.
Oh, I see. Okay. I see. So you need basically this condition on Q over M to get a non-singular horizon.
Right.
Yeah,
That's right.
Just to say something, the red line is where that condition is being saturated. And so if Q is 0, that's never happens.
Yeah, but I was trying to reconcile that with what Gary said in the beginning. I should have asked maybe when he showed the red line. But okay, I see. So along that red line, you have nice non-singular black holes.
Exactly, exactly.
And Gary, sorry, I should wait till the end of the talk, but just to ask it, I mean, the puzzle, which I'm sure you'll get to is, let's say you were along that part of the curve for the entropy and temperature where the specific heat is positive, and it seems that you can arrange parameters so you have a nice big black hole, you know, all corrections are small. Why does this object stop radiating? Okay.
That's exactly where we're going.
Okay, thank you. Sorry.
Just wait a couple minutes.
Yes.
Okay. So this is a plot which shows the features that I was just talking about. So I again plot Q minus M on the vertical axis versus M on the horizontal axis. And these curves represent changing Q over M with alpha equal to 1. So the red curve is exactly the one we've seen before. And these curves to the lower left here just increase the charge to mass ratio according to this scale on the right. And what you see is just what I said. So first of all, as soon as Q over M is bigger than 1, the hairy black holes, which exist under these curves, don't exist past a certain mass. So they only exist for small mass, so that you have strong enough electric fields to trigger the instability. Also, this minimum mass on the these maximal wormholes here, this minimum mass gets smaller and smaller, and as soon as, well, this green curve, which is only like 1.1, as soon as it's 1.1 or bigger, this whole maximum charge black holes are non-singular. You don't have any singular limits here. But there's a third feature, which I didn't mention before, and is a little counterintuitive. You see that the maximum charge you can have when you increase Q over M goes down. And when you get to this yellow curve, which is like 1.3 in this Q over M ratio, the maximum charge falls below M. And so in this region, you don't have maximal wormholes. The black hole with maximum charge would be the good old Reisner-Nordstrom with its usual extremal limit. But in this region, in a theory with Q over M equals 1.3, you would find that Reisner-Nordstrom would still be unstable at a charge around here. It would develop scalar hair. The scalar hair would exist, but then when you push farther to larger charge, the scalar hair disappears and the maximal charge solution is the usual extremal Reisner-Nordstrom. So that's what happens when you increase Q over M. When you decrease Q over M, well, there's a plot here with Q over M 0.994. You see this blue curve, which, as I said, now has an upper limit. The black holes can't be more massive than this, and the lower limit has increased. And this sort of finite range where you can have these maximal wormholes get smaller very quickly. And as I said, as soon as Q over M drops below 0.99, you just don't have any. The boundary is then singular. Right now, there's a singular boundary extending from here out to infinity and a singular boundary on the other end going back to the origin. But once you decrease Q over M less than 0.99, then the boundary is singular everywhere. Okay, so now I see I have only a few minutes left. Let me discuss Hawking radiation and what happens when you have one of these extremal, or these new maximal.
Gary, we're very flexible with time, so please don't hurry. Please take the time you need.
Okay, well, okay, let me finish this and then you'll tell me how much time I have to talk about the interior. Because
a typical seminar can easily go 2 hours, Gary. So you're doing
really
well, actually, yes.
Oh, wow. Okay, so I will be able to tell you about the interior.
Right.
Okay, this is great. Okay, let's first do the Hawking radiation. So why doesn't Hawking radiation turn a maximal wormhole into a naked singularity? So let's first consider the case I started with, the coupling alpha equal to 1 and Q equal to M. And the temperature of these maximal wormholes is low, so you don't expect to thermally create these massive charged particles. You expect them to be created near the horizon by a Schwinger mechanism. So you have some production rate, which is the exponential of minus pi m squared over QE, where E is the electric field on the horizon. Photons are going to be massive inside this charged scalar condensate, so they're suppressed, but gravitons are not, and so we expect gravitons will be produced thermally. So at least naively, you expect the black hole to lose mass but not charge, and this is essentially a vertical line in the phase diagram, which ends on a maximal wormhole. So let me just remind you, I plot Q minus M here versus M. So if you decrease the mass and don't change the charge, you might expect that you follow a curve which moves off in a diagonal, because you're decreasing the mass and also and increasing Q minus M. Mm-hmm. But when you look at the scale, the scale on the mass is the usual 1/2, 1, 1.5, and the scale on the vertical axis is tiny, 0.005, 0.01, 0.015. So any noticeable change in the mass is going to be a huge change in this vertical axis. So if you're here and you decrease the mass, you do basically go straight up into this maximal wormhole. Okay, but the resolution is that the charged particles are not really exponentially suppressed, because we've assumed that Q over M is 1. And if you look at the plot I showed earlier of what the electric field is at the horizon, that's also of order 1 in these units. So the Schwinger pair creation is not really hugely suppressed. On the other hand, the temperature for these black holes is small, 10 to the minus 2, 10 to the minus 3, something like that. So thermal production of gravitons is suppressed. T to the 4th is some very small amount. So we expect the late stages of Hawking radiation to be dominated by production of these Q equals M particles, which should keep, the black hole charge Q minus M approximately constant. And this is just a horizontal line in our phase diagram ending in the singular solution. Okay, so what I'm saying is that if you're producing Q equals M particles and you start someplace, you're going to Hawking radiate along a curve which more or less goes horizontally, ending in this singular boundary. And you're not going to end on the maximal wormhole.
Right.
Okay, so here is some properties of hairy black holes. If you keep, okay, so alpha is 1, Q over M is 1, and we're keeping Q minus M fixed at some value. And what you see if you Hawking radiate, again, the entropy goes to 0. The temperature, again, has this non-monotonic form where it starts to rise and then falls to 0 as you approach the singular limit. The charge on the whole singularity, of course, it becomes very, very singular.
Okay.
Other cases with alpha equal to 1, what happens if you change the charge to mass ratio? Well, if the charge to mass ratio is bigger than 1.1, I showed you that there are no singular extremal black holes. You have the hairy black holes always have a non-singular maximal wormhole endpoint. But Hawking radiation is again likely dominated by charged particles. And since the charge is bigger than the mass, if you radiate these particles, Q minus M will decrease. You decrease the charge faster than the mass. And so you move away from this maximum charge black hole. So the black holes evolve away from extremality. If Q over M is less than, well, 0.99, then Q minus M must increase because you're losing mass faster than charge. But there are no maximal wormholes in this case. The upper limit, I said, was singular everywhere. So in all these cases, you never turn a black hole into a naked singularity. You never actually evolve toward a maximal wormhole. But increasing alpha actually lowers the electric field on the horizon and increases the temperature for these maximal wormholes. When you get close to alpha equal to 100, I didn't show you the curves, but the temperature is much larger and the electric field is smaller. And in this case, the radiation will be dominated by gravitons. And we have to ask what happens. So for large alpha, we do expect to evolve toward a maximal wormhole. The black hole is losing mass, but not charge. The horizon will shrink, and this parameter mu, the electrostatic potential, will increase. But mu is already at its maximum possible value. And so further evolution will cause the scalar to become unbound. So at this point, I think either the scalar radiates away to infinity just enough charge so that you return to a mu equal to 1, and the evolution basically follows this mu equals 1 curve down to small mass. Alternatively, this might destabilize the scalar hair completely, and all scalar hair is radiated away, leaving just a Reisner-Nordström black hole. This will happen only if the Reisner-Nordström black hole you're left with is stable. Or there could be something in between, that you might radiate part of the hair, but not all of it, and return to something that can then radiate some more non-zero temperature and not maximum charge. And unfortunately, we don't know the answer. At this point, these seem like possibilities. Let me then conclude this section with the open questions, one of them being just what I asked. So what option actually follows when these maximal wormholes Hawking evaporate? How much of the scalar hair gets radiated away? What characterizes the class of theories with maximal wormholes? When can they occur? We've given one example, but there's undoubtedly others. Can they exist in more than 4 dimensions? I suspect so, but we haven't looked at that. Are there asymptotically anti-de Sitter examples of these maximal wormholes? And if so, what are the implications for holography? We know this doesn't happen for the simple holographic superconductors that have been studied before. The singular limits in those cases the extremal limits in those cases are singular. But maybe there's, with a few extra couplings or something, you might find some analogs of these maximal wormholes. And finally, it's been shown that, the question is, how does rotation affect the maximal wormholes? It's known that Kerr black holes can develop massive scalar hair near extremality, even without any additional interactions. This was shown back in 2014. So just an ordinary massive scalar field, neutral scalar field, coupled to gravity, can give rise to hairy rotating black holes. And so you can ask, can an extremal limit of this rotating black hole have non-zero temperature because some boundary condition required for the hair gets saturated before the horizon becomes singular? So let me stop and ask if there's any questions about this. I'm out of time, but you said I can keep going. So I will tell you about the interior, but if there's no more questions about this, this part.
Sorry, Gary. Now,
Yeah.
I think I'm a bit confused. Please excuse me. But so are there then bottom line known examples in your class of models where you have a extremal limit, which is a warm black hole, and even after accounting for pair production, it stays non-singular in a stable way? Or was I right that, like the alpha equal to 1 case, I thought finally because of pair production evolved towards a singular solution?
Right. So the alpha equals 1 case does, but the case with large alpha is different. That was the point. So I had this plot earlier where I had alpha going up to 100, and I showed you the curve with maximal wormholes in that theory. And in that theory, as far as we can tell, I mean, I should emphasize, we've not done detailed studies of Hawking radiation with gray body factors and all of that, but just simple estimates using the Schwinger pair creation rate and thermal production and stuff suggests that in this case, yes, Schwinger pair production will be exponentially suppressed because the electric field is just not big enough on the horizon of these big black holes. And the temperature has increased to a point where the gravitons are not suppressed so much. So this is a case where we do expect that Hawking radiation will evolve toward a maximal wormhole. And what happens in that case is, as I said, I think that the scalar field will just become unbound because you will be effectively trying to increase mu past these, asymptotic condition.
I see. Oh, thank you. Sorry, I didn't absorb that first time around. Okay.
Yeah.
Thank you.
Sorry, Gary. Suppose we look at a situation that's above your red curve, and we construct one of your static black hole solutions with the scalar growing towards infinity.
Okay, so sorry. Let's solutions above the red curve.
Yeah, the red curve is the extremal wormhole curve, right?
Extremal wormhole curve,
yes.
Right.
So we look at some scalar solution that's above the red curve. And as you said, it has a scalar field growing exponentially to infinity. Now, I take that solution at r equals 10 times the event horizon, I change the scalar field so it now starts coming down and goes to 0. I just look at a configuration in which I'm doing this.
Okay.
So this is, of course, not a solution, but we can use it to set up some sort of initial condition for general relativity. Okay. And I was wondering where you expect, the question of where this evolves to, just classically, sounds to me like some sort of proxy of your question about what Hawking radiation does, because you've produced a black hole inside, which is above where you want to be, but at infinity it's where you want to be because you've just arranged that by hand.
Yes.
So now if you could set up an initial condition like this, there's a question of classical general relativity. Where does this evolve to? And perhaps you would say that it would end up evolving to radiating charge off to infinity and settling down to your wormhole. Would this be your guess?
Yes, I think. Oh, so you want to keep the black hole, keep everything, but just take the scalar field and cut it off near the horizon.
Yeah, in some smooth way. In some smooth way, and bring it down to to zero. So it's a nice normalizable finite energy configuration, but locally it's in the region you don't like, right?
Right.
Okay.
Oh, I see. So you're cutting it off at infinity, but at large radius where it's unstable. And,
that's right. So I cut it off at r for r greater than 10 times the event horizon, let's say.
Yeah. I see. Yeah, that does sound like a good proxy for what it will help us see what this evolves into. Yeah, does it radiate a little bit and settle down back to a mu equals 1 solution, or does it keep going?
Yes, and this is a question that it maybe even is practically answerable, especially given the expertise of your collaborators. I mean,
yes.
You could. Okay.
Yes. No, I understand. I think that's a good point. Yeah, we'll look into that.
Thank you.
Yeah, I have two questions. One about these 3 possible outcomes you just gave about Hawking radiation when alpha is greater than 1,
Okay.
very large. So in any of these outcomes, no matter what possible outcome is true, is this black hole can never give rise to naked singularity? Is that right? I understand
Well, that is our guess. Yeah, that is our suspicion that we will never turn the black hole into a naked singularity because we have this option. I mean, when I first realized that we had these black holes with maximum charge and non-zero temperature, I was worried. I thought that sounded likely that we would turn a black hole into a naked singularity. But after thinking about it, and we have these other options, this seems much more likely that the scalar hair will just destabilize, radiate, and you won't end up with a naked singularity.
Okay, and the second question is, can we find some similar solution of maximal wormholes kind of solution in asymptotically area spaces?
That was one of my unknown. So here is open questions. And are there asymptotically ADS examples? I don't know. I mean, we just found these in this one theory, a few months ago. And so I don't know. There's, yeah, I think people need to look at other possibilities.
Yeah, actually, if you can hear me, I have a small question.
Yes?
Yeah, so all these solutions depend on very delicate choice of your parameters, so ratios. So are these numerical solutions, or do you have some analytical expressions for all these fields in the background of black hole background?
Right. Now, these are numerical solutions. So what we found, we constructed these solutions numerically. We don't have analytic expressions for them.
But they are valid from r equal to 0 to till the infinity, asymptotic infinity.
Yeah. So you can put boundary conditions at infinity and boundary conditions at the horizon and solve. You can compactify the region into some finite region for numerics. So you can do that.
Okay, thank you very much. Yeah.
Okay.
Sorry, just one small clarification about the point, that question about ADS that you answered. So, so if we keep this additional coupling, this alpha in your game, is it true that we'll not have an analog of these solutions in ADS? It's guaranteed, or
no,
that is up to investigation? Like
no, I haven't looked at it.
Okay.
I haven't looked into it. Of course, the asymptotics are different, so the asymptotic conditions will be different. We just haven't looked at the ADS case yet.
I see. All right.
Okay.
So could I make a quick comment about that, please?
Please, yeah.
If in ADS we violate the superradiance bound, that leads to this instability which typically leads to these hairy black holes.
Right.
So I would expect that that basically in ADS, what would happen is that if you went past this line, you would just eject hair out into some atmosphere, eject some scalar field out into the atmosphere outside, and would settle down into one of these, the standard hairy black holes.
Okay. But the question is, okay, we want to keep increasing the charge for a given mass and see what the properties of the maximum charge. Now, I agree that there won't be the instability. There's no place to radiate away the scalar hair too in ADS. So
yeah. So it sounds a bit like there are two qualitatively different kinds of instability. Maybe they're not quantitatively different. Maybe there's no order parameter between them. But one is your brighter Lohner-Friedman kind of thing.
Right.
And then there's the superradiance instability.
Right.
Right.
And that's really different.
These are sort of qualitatively different. I'm not sure quantitatively. And one would take over when the other, continuing to just give you some halo, I would have thought.
Uh-huh.
Yeah.
Okay. No, I agree there are two different types of instabilities, and yeah, that'd be interesting to see what happens. Okay. Well, you said I should keep going, so I will. Tell me when you want me to stop. But the last topic I wanted to tell you about was what happens inside the event horizon on these black holes. And what you find is that just after the onset of scalar hair, so I'm going to change my focus a little bit from the sort of maximum charge to the charge where the instability first sets in. So just past that, when the scalar field outside is tiny, boring, and doing nothing at all, the effect on the interior is enormous, and the interior has a sort of very interesting dynamics. We identify three distinct epochs, which we call the collapse of the Einstein-Rosen bridge, Josephson oscillations of the scalar field, and then finally a Kasner epoch, which can possibly include transitions to new Kasner epochs. You will show that there is no Cauchy horizon. So the usual inner horizon of Reisner-Nordstrom is removed as soon as the scalar hair turns on. There's a final space-like singularity, and the nature of that singularity is extremely sensitive to the charge to mass ratio of the black hole near the onset of the scalar hair. So I'm going to explain all of this, but I should point out that very similar behavior was seen inside a holographic superconductor about a year earlier. This is work I did with Hartnell and Kruthroff and George Santos. So in that case, of course, we had the asymptotically ADS boundary condition. We didn't have any extra couplings. And one of the motivations for looking at the black holes I've been talking about was to try to find an asymptotically flat analog of the holographic superconductor. So we wanted asymptotically flat black holes which turn on charged scalar hair when you increase the charge. And we were curious whether the intricate dynamics that was seen in the holographic superconductor is also possible in the asymptotically flat context, and we found that it is. Okay, so let me now briefly tell you about these different epochs. So I'm going to choose a new ansatz for the interior. The vector potential and scalar field don't change, so we'll describe them as we did before, but the metric ansatz changes. So first of all, we're going to write the two-sphere. We're still considering spherical solutions, but we're going to write the two-sphere in this form with kappa equal to 1. And the reason for writing it in this way is that keeping kappa helps us to more easily identify terms in the equations of motion coming from the curvature of the sphere. We've also factored out an overall R squared and written it in terms of this parameter z. So we define z to be R plus over R, and we're going to set f at z equal to 1 equal to 0. So that means that z equal to 1 is the event horizon for these black holes. So our two metric functions are f and chi, and we've just chosen this, this slightly different ansatz. So we have four functions to solve for. We have f, chi for the metric, and capital phi and psi. And they satisfy these four coupled ODEs. So in terms of dimensionless variables, q tilde for the ratio of q over m, and y plus, which is basically a dimensionless version of this horizon radius, you get the following equations. Okay, so they're very messy and you don't need to worry about the details, but Maxwell's equation is in the first line, the scalar equation is the second line, and then the last two equations are two components of Einstein's equation. Now, okay, let me first show that there cannot be a smooth inner horizon once the scalar pair turns on. So you can show that those equations I just flashed imply that this particular quantity, this combination of the fields, is constant. It's independent of z. Now, at a horizon, this metric function f vanishes, and the equations of motion involve lots of terms with 1 over f. So to have a smooth horizon, these are constants, but it follows that either the scalar field must vanish or this the electrostatic potential has to vanish at any smooth horizon. But if you choose psi to vanish, then by taking derivatives, you find that all derivatives of psi must also vanish. And that's not what we want. So we're going to require that phi vanish at the horizon. So if you evaluate this constant at the event horizon, phi is 0, so this term goes away. The last term is an integral from the horizon to the interior, to larger z. So if you evaluate it at the horizon, that's 0. So you just get the first term, and the derivative has to hit f, because of course f is 0 there. And at the event horizon, f is decreasing because it's positive outside the horizon, negative inside the horizon. So you find that this constant c1 must be negative. But now we evaluate it at an inner horizon. So if there was a smooth inner horizon, f would have to be increasing from its negative values to a positive value on the other side. So if we evaluate c1 there, we now get a positive contribution from the first term. We get an integral of a positive quantity, which is also positive. So we conclude that the constant must be positive. But of course it's constant, and so that's a contradiction. So once the scalar hair turns on, you can no longer have a smooth Cauchy horizon, and space-time always ends in a space-type singularity. So our strategy for solving the equations of motion is to start with data on the horizon, which I said is z equal to 1, and numerically evolve to large z. And near the onset of the instability, I'll call that QC. So for any mass, well, for the parameters in the theory and for any mass of the black hole, there is some QC where the black hole becomes unstable. And we're going to look at Q just bigger than that. So for Q near QC, we see distinct features. And to understand them better, we drop terms in the equations of motion that are negligible during this region of interest, and then find analytic solutions to the remaining equations. And then we check that the solutions of the full equations agree with our analytic approximations in the appropriate region. So that's the strategy we followed. And the first feature you see is a collapse of the Einstein-Rosen bridge. Okay, so for Q slightly bigger than this critical charge, the scalar field, which is 0 well, not 0, but small everywhere outside the horizon, stays small inside until it approaches the former Cauchy horizon. Then it changes rapidly, causing a large drop in GTT. Now remember, T is a space-like coordinate inside the horizon. And if you think about the Einstein-Rosen bridge connecting the two asymptotic regions, GTT is basically telling you the length of that Einstein-Rosen bridge. If it becomes small rapidly, then that bridge in some sense is shrinking. And we called it the collapse of the Einstein-Rosen bridge. In this region, if you look at the terms that are important, you can actually derive a decoupled equation for GTT alone. And I wrote that equation here. It involves a constant C1, which is very small because it's proportional to the value of the scalar field on the horizon. You can solve that equation, and the solution is written here. And what that means is that you get the following behavior. So Z naught and C2 are two other constants. So those are the constants of integration for solving the second order equation. If Z is less than this constant Z naught, what that means is the right-hand side is positive. Well, GTT is positive inside the horizon, and C1 is small. So basically, the first term is negligible, and GTT is just linearly going to 0 as Z approaches Z naught. But for Z bigger than Z naught, the right-hand side becomes negative, and that means the first term dominates. And what that implies is that GTT actually is exponentially dropping off in Z. So it takes the behavior of e to the minus this constant times Z minus Z naught. So it's starting to fall linearly, and then it starts falling exponentially. And that's what we call the collapse of the Einstein-Rosen bridge.
Gary, how does the Penrose diagram look like?
The Penrose diagram, it looks like Schwarzschild with a space-like singularity. So in other words, in terms of the Penrose diagram, well, the space-like singularity, yeah, I guess I was going to say it might bow out a little bit more than we usually draw it in Schwarzschild. I'm trying to think if that's probably not meaningful, so don't worry about it. No, in terms of causal, these are metric features which are not going to really affect the causal structure. The overall Penrose diagram will look like Schwarzschild.
So the other second exterior is still there, but
yes.
Okay, so when you say that this collapse of the Einstein-Rosen bridge, I mean,
I have a cutoff in mind. So you're right, it doesn't really collapse. You have the asymptotic region, so it still goes from one side to the other.
Right.
It's just that if you think inside the horizon, if you take a surface of constant radius or a surface of constant z in the coordinates I'm using, and cut it off at some large, t and some small t, large negative t, large positive t.
I see.
You just take that piece and say, well, how big is it? If GTT goes to 0 rapidly, that's going to shrink rapidly.
I see.
That's all we mean.
Okay, thank you.
Okay, so here's an example for some choice of parameters, which I've listed here. Okay, so what I'm plotting here is GTT as a function of z. It says z over zh, but zh at the horizon is 1, so this is basically z. The solid line is the numerical solution of the full set of equations. The dotted line is the approximate solution I just showed you. And you see they agree very well in this region. The scale here is logarithmic. So it starts falling slowly and then approaches this exponential drop off here. Also notice that z is pretty close to 1. This is happening when z is about 1.1, 1.15. And that's because the instability doesn't start until you're very close to extremality for the original Reisner-Nordstrom black hole. So Q has to be close to M before you hit this sort of onset of the instability. And that means that the sort of radial coordinate for the inner horizon is close to the radial coordinate for the outer horizon. So you don't need to go far in Z to reach what used to be the inner horizon. On the right, I show what psi is doing, the scalar field. Whoops. We also have an analytic approximation for psi, which is more complicated. I didn't show you, but the solid black line is the solution to the full numerical solutions. The dotted one is the solution for our analytic approximation. Again, it's working very well. So now we come to the next phase. So after the collapse of the Einstein-Rosen bridge, one finds that psi essentially satisfies the Bessel equation. So you can write it's a solution, an approximate solution for psi in terms of the two solutions of Bessel's equation. C4, C5 are just the coefficients. And the argument is 1 over z squared times a constant. The constants involve, okay, C3 is a large constant. You can show it's proportional to 1 over C1 squared, and C1 was proportional to the scalar field on the event horizon. So C3 is very big. And phi naught, well, in this regime, you can show that the electrostatic potential phi is essentially constant. So we call that constant phi naught. And since AT points in a space-like direction inside the horizon, T is a space-like coordinate, you can view this constant potential as just a phase winding of our complex scalar field. And the fact that this phase winding causes oscillations of psi is a familiar feature in superconductors. It's part of the Josephson effect. So we call these Josephson oscillations of the charged scalar. You can also get an approximate solution for F in this regime in terms of psi. So that's written here. It's z cubed times some exponential of some integral involving psi. And I want to note that our new coupling alpha doesn't appear in any of the approximations I've shown you so far. So those terms which depend on the new interaction are basically negligible in this evolution. And these two phases are almost identical to what was seen inside a holographic superconductor. Before we considered planar black holes, but the curvature on the sphere isn't playing much of a role here either. Okay, so here's a check of the Josephson oscillations. I'm plotting on the left psi as a function of z. And this is basically the Bessel functions, the damped oscillations of the Bessel function. The solid line is, again, the full numerical solution. The dotted line is a solution of our the approximate of the Bessel functions. On the right, we have a plot. It's actually convenient to plot not f, but a logarithmic derivative of f. So it's z f prime over f. And again, you see pretty good agreement there. Okay, third regime, the Kasner epoch. At the end of the Josephson oscillations, psi grows logarithmically. And we can write it as some constant beta times log z. That just comes from, that comes from this term, right? At large z, you're approaching 0, and the argument and this second Bessel function diverges logarithmically as the argument goes to 0. So the constant beta is proportional to this constant C5 I wrote there. But it'll be convenient just to write psi as a constant beta times log z. Now, you can show that if the scalar field is evolving logarithmically, the metric components all evolve as some power of z. And that's called a Kasner epoch. Because the original Kasner solution is a homogeneous anisotropic vacuum solution of general relativity found long ago, which takes the following form. In terms of some proper time tau, you find the metric components are just powers of tau involving these 3 exponents, px, py, pz. And this metric is Ricci flat if the sum of the exponents is 1 and the sum of the squares is 1. You have 3 exponents and 2 conditions. So there's a 1 parameter family of these Kasner solutions in general relativity. Now we have not a vacuum solution, of course, we have a charged scalar and a Maxwell field. But when the Maxwell field and the sphere curvature are both negligible, there's a Kasner-like solution to our equations. If we convert z to proper time, that solution takes the following form with some power of pt and px, or the metric. The symmetry on the sphere says that the exponents in the dx and d phi directions has to be the same. We have a scalar field evolving logarithmically, so that gives us another coefficient p psi. And this will solve our equations, or our sort of charged scalar metric equations, if the sum of the exponents here is 1 and the sum of the squares is 1. The factor 4 is just due to our normalization of the scalar field. So we added one more parameter for the scalar, but we took away one from the metric because of the symmetry. So we still have just one parameter family of solutions. And using our z coordinate, I mean, writing psi as beta times log z, we can use beta as our parameter for this Kasner epoch. And the exponents that you see here are all functions of beta, which I've written down. You can check that these expressions satisfy our two constraints. Now, in this Kasner phase, the Maxwell potential evolves like this. It's basically a constant plus a power of z over log squared z. So this exponent, 1 minus 2 beta squared, and these ek and phi k are just constants. So if beta squared is bigger than 1/2, and I'll remind you that means if beta squared is bigger than 1/2, pt is positive, and that we evolve toward tau equal to 0. That's the singularity in Kasner. So that means that GTT is shrinking. So if beta squared is bigger than 1/2, the Maxwell field, if it's small initially, is just going to stay negligible. It just gets smaller and smaller as you evolve to large Z. So in that case, we can look at these solutions. The beta turns out to be an oscillating function of the black hole parameters. And near QC, the critical charge, it's very well fit by this expression. So A, B, and C are constants. It's just sine of beta over Q over QC minus 1. So this oscillates very rapidly when Q approaches QC. And here is a plot of that. I'm plotting beta, the coefficient of the log in the scalar field, as a function of Q over QC. You see how small this is, starting from 1, 0.00005, making very, very small changes in Q. Again, the solid black line is the solution of our full equations. The dashed line is the just that simple sine function I showed you a moment ago. This is for the range of parameters alpha 1, Q over m equals 1. The mass is 1. And here, just to tell you, I give you the value of the critical charge. So if you take Reiser-Nordstrom with a mass, say 0.5, the charge has to be 0.494 before you trigger the instability. So it's close to extremality. You go just slightly above it, and you get these, you get this Kasner regime with a value of this parameter. Beta is the one parameter in the Kasner regime. And that Kasner regime is, well, essentially infinitely sensitive to Q near QC. So that is why we say that there is this extreme sensitivity to the black hole parameters near this onset of the scalar potential, the scalar field. Okay, it's getting late. I'm going to, well, let me ask. I could sort of finish up now, or I could keep going. How do people, what do you think?
Yeah, up to you, Gary. You can keep going if you want.
All right, well, I'll go. I don't have a lot more. I just have a little bit more. So I guess if you don't mind. So I said if beta squared is bigger than a half, the Käsner epoch continues all the way to the singularity. But if beta squared is less than a half, the Maxwell field is going to start growing. And what that does is it causes a transition to a new Käsner epoch. It changes beta. And this transition depends on alpha. It's not a, so this is where the new term comes in. So here is some examples of this transition. I'm plotting z times psi prime, which is, well, essentially beta. When this z times psi prime is constant, it means that psi is a constant times log z. So that's what we're calling beta. So every time it's constant, it's a beta. But this is the actual evolution of z psi prime. We start with curves of various values of beta, 0.08, 0.1, 0.12, all values where beta squared is less than a half. You evolve, it's constant for a very long time. Look, z is 10, this is logarithmic, this is 10 to the 13, 10 to the 15. So you evolve for a very long time in z. And then finally, the Maxwell field grows enough, it triggers a transition, and you evolve to a different, different range. Changing beta in this way corresponds to changing the charge on the black hole by a tiny amount, only say 1 part in 10 to the 7. So it's very, very sensitive. But I should emphasize that here we had beta oscillating as functions of q. Beta squared is less than a half if beta is like 0.7. So in each oscillation, when it's above 0.7 or less than minus 0.7, you hit a Käsner regime, which continues with that beta all the way to the singularity. And all these other values of each oscillation, when beta is less than 0.7, you evolve for a while with that beta, and then you transition to a new beta. So you have interesting, and sensitive dynamics in the evolution in Z, as well as in changing the parameters of the black hole.
So, sorry,
okay, I'm going. Go ahead.
Sorry, Gary, I might have lost the thread. Please excuse me, but basically, as you are changing Z, your Z is like your coordinate tau in a sense. Is it? That is.
That's right. Yeah.
Okay. And so what happens in these cases, just to understand where the Käsner exponent starts to change? Are there a finite number of transitions before you hit the singularity, or what happens to the system?
It depends on the precise value of Q, of the black hole charge. Yeah. You can have one transition for some Q, you can have 2 transitions. I mean, in fact, that's what I'm going to tell you next. This next slide was all about how after the transition, beta squared might still be less than 1. And sorry, less than a half. And so here's an example of a transition where you get beta, beta starts at minus 0.42. And you get all these different values of beta, some positive, some negative. And so some of them are going to have beta squared less than a half. Nice. But to get this, here I'm plotting what the Q value was. And even multiplying by 1,000, these numbers agree to 7 decimal points or something. So you're changing Q by 1 part in 10 to the 10 in this case to see this effect. So it's incredibly sensitive. And by fine tuning Q even more, you can get 3 transitions, 4 transitions, etc. It's just.
This sounds amazing. I'm sorry, I know nothing about numerical work, but if it's being done, is this, can one estimate this sensitivity analytically, or is the numerics under enough control to be able to see this sensitivity, Gary?
Oh, the numerics is certainly under control. I mean, yes, I mean, I have to say this is all done by George. This part, he's just incredible, and you can, yes, you can work to very high precision. You introduce new variables. You can work with log z and not z and things like that to get to very large values. But this, so this is numerical, and and it's incredible. Yeah, so George did a
I see.
fantastic job to dig this out of the solutions.
I see. Thank you.
Okay, so I'm almost done. Let me just say I've been talking all the time about what happens inside the black hole when Q is very close to QC. So I just wanted to show you one example when you go from the onset of the scalar hair to the maximum value, maximum possible charge. And this is a case where the maximum charge is singular. So this is, say, one of the Kasner exponents. Now I'm just calling PT, the exponent in GTT. Again, as a function of Q over QC. So Q close to QC, these are those very rapid oscillations we saw before. But now you see the structure farther away from this onset. And there's still interesting features here, which we don't understand. I think I do understand the end. The end here, PT goes to 1 as you approach the singular extremal limit when Q approaches Q max. And that you can understand because the singularity, the space-like singularity, actually moves down and approaches the event horizon. PT equals 1 means that you're basically approaching a null surface. And so that's what's happening there. And finally, I want to go back to the maximal wormholes because what we did is we went back to that red curve from the very beginning of the talk that I had when we were looking at maximum charge, and this maximum charge was not singular, finite temperature. We looked inside those black holes, and this is what PT does as a function of the mass along that red curve. So again, at the lower limit is when the maximal wormholes become singular, when they approach the singular limit. And here again, PT goes to 1. The curve, the singularity is again approaching the event horizon. At the other limit here, for large mass, I mean, you can't see it too well, but the oscillations I think are partly because the maximal charge now is approaching the onset charge. For large mass, all of them approach M. And so you might start to see the oscillations that we saw because Q is close to QC. All right, one final comment. Our discussion has been entirely classical, and we certainly expect quantum effects to become important near the singularities. They're also going to become important when the Josephson oscillations become too rapid. The frequency becomes infinite. That will produce large curvature, and quantum effects will be important there also. But even staying away from Planck regimes, we find it remarkable that adding a tiny amount of scalar hair outside the horizon has such a profound and sensitive effect on the geometry inside. So to summarize, we've studied black holes in an Einstein-Maxwell charge scalar theory with a psi squared f squared coupling. We found that increasing Q at fixed M causes Reiser-Nordström to develop scalar hair. The black hole with maximal charge can have non-zero temperature. That's what we call maximal wormholes. Hawking radiation probably does not cause the black hole to turn into a naked singularity. And there's intricate dynamics inside the horizon. And I'm going to stop there. And thank you for listening.
Let's thank Gary for a very nice talk. Questions?
So, sorry, Gary, I'm sorry for being so dense, but if I can just go back to the exterior of these black holes and just go back to that case, alpha, mod alpha, I guess, greater than 1, just to absorb what you said. So my understanding was that in that case, when the black hole starts evolving, it mostly, say, gives out gravitons, etc., if I'm right.
Yes.
Okay.
Yes.
All right. And then, and here's the part I didn't quite absorb. Was it that it went more? So let's say we start with the case where you don't have the super radiance instability. So Q mu is less than M, as you emphasized. Then does it move towards Q mu becoming more towards M? And finally leading to a sort of onset of this instability in that you can then start shedding the scalar hair. Was that the picture, if I got it right?
That was exactly the picture. And so let me just say it again. So we imagine some black hole. So in this theory where we have, say, alpha very large, alpha, so say 100, and I was saying that the electric fields are small and the temperatures are big, so that we expect to dominate a radiation dominated by gravitons. Okay, so if we have some hairy black hole over here, it will decrease mass and move up. And now at this point, what I said was it's going to want to continue to radiate gravitons, and that will shrink the horizon. And by shrinking the horizon, you increase the electrostatic potential difference between the horizon and infinity, causing mu to grow beyond 1. And that's the source of this, causing the scalar hair to become unstable.
Okay.
That was the argument.
Thank you. Thank you very much. Thanks a lot for a great talk. Thank you.
Okay, well, maybe I will stop sharing and.
Okay, so are there any other questions? No.
Sir, just a very, very vague question that may make no sense. The difficulty in finding this, just going back to the exterior again, the difficulty in finding this solution when you had when you had q mu greater than 1, the difficulty in finding the solution that went off to infinity was that you were trying to find a solution that had no time dependence, right?
Right.
If you allowed the scalar to oscillate at infinity, you would this problem of the exponential rise would not happen, presumably.
Well, wait a minute. So you're assuming that we violate this asymptotic condition, right? So
yes.
And we look for so we look for static solutions because we want the sort of hair. And if you violate that condition, you find static solutions which oscillate. So rather than the exponentially damped, you get oscillating solutions at infinity, which are static. But the problem is that would then correspond to infinite energy, right?
So this was oscillating in space.
Oscillating in space.
I was wondering if you allowed oscillations in time.
Oh, I see. I see what you mean. If you allowed oscillations in time, you're saying, could you stop it from growing?
I'll tell you what I was thinking. What I was thinking was that just this A0 at infinity, if this is what's causing it, is sort of like a gauge thing. You can gauge A0 away at the expense of having some oscillation in time. So I was thinking that if you allowed that, that you might be able to. It's just very big.
I see. I see.
Well, of course, then, you wouldn't get a stationary, I mean, just to say it another way, whether a solution is stationary in the sense of time dependent or not is a gauge thing, right? You could always do a gauge transformation everywhere. So if the solution had the same oscillation in time everywhere, that's also in some sense stationary. It seems to me that what the solution wants to do is to have different time dependencies in different places.
Yeah.
And that's what's causing the trouble, right?
Yeah, I mean, if what you're saying, if I understand, because A0, you're choosing the gauge where Gary chose the gauge where A0 vanished at the horizon, then this effect wouldn't be there, but it's there at infinity. And if you take it away at infinity, then you'd get that time dependence.
Right. I don't even know what the question is, but I was just wondering whether this. It's probably informal. Yeah.
Well, I think it's a very good question, and we really didn't look at the time-dependent case, but we should. So I think I will try to think about that and get my collaborators to think about that. Maybe we'll have some answers for you next time we meet.
Okay,
that would be great.
Okay, if there are no further questions, let's thank Gary again.
Thank you, Gary, for a great talk.
Okay. Thanks.